All right. Good morning, everybody. We are the last day of our workshop, so there's not much to say. Get Anchi to talk about. Anchi will talk about things of refinement. All right.
Okay. So I expand my talk a little bit. Not just talking about detail refinement, because that probably will take 10 minutes, and then also, give you some overall view of what detail means and the type of details that we have. That's not necessarily included in the detail refinement. The refinement procedure was published in the 1986 paper by Richard Henderson et al. And you can find a lot of earlier references from there. And there are some really a really good book has been published recently. I forgot which year it is, and by Bob Glaser and a group of people. So there are a lot of mathematical things in there, but overall it will give you a very good feel on what detailed is and all the other theoretical part of things that we do. Okay, the different type of details. The first one is, so just think of this a little bit like a light. Then you have a light source. If the light source is a point, then if you have perfect length, then you get a parallel beam straight down if you align it right. So the first type of beam tilt will be caused by the finite size of the source. So that's the first kind. And the second kind is, of course, if the whole axis of your illumination is not aligned with your length. And then the third type is a divergence of the beam, which is not accounted for. So if it doesn't come with parallel beams, then it cannot focus to one point. So basically that's what it's saying. Even if you have a perfect length, that's work for one. And there's a fourth type. It's sort of a spiral tilt. This only comes about because the way electrons travel, it doesn't actually travel straight down in the column of the Tn. It actually goes down in sort of a spiral fashion. So there is a little bit of tilt in that direction. So you can imagine if there isn't such a thing, then it would just circle in the same plane, never go down in space. So it has this kind of a spiral type of thing, and that creates a sort of a off-plane tilt to it. So that's another type that's specific for electrons. This will be true for visible light as well. So the amount of beam tilt that's been seen in our type of microscopes are different for each one of those. This is the smallest one in general, unless you basically use spot one, open up all your condenser aperture and everything. You might get this a little bigger, but from what I understand, that we are not yet reached the point that we need to worry about this. People doing material science, they want to look at the sub-angstrom resolution, then they have to worry about it. And this is commonly being seen. And when you use a microscope, you probably all do rotation center alignment. That's the alignment of what we call the axial beam tilt to the axis. So that particular alignment can get you to about 2 million radians easily. And then if you are very good, you may be 1 million radian of beam tilt. Then there's a second alignment called the coma-free alignment, which is really a refinement of that beam tilt, so that it will satisfy to the parallel beam in this condition. Rotation center is mainly deals with that it doesn't tilt as you change defocus. This mainly deals with that it doesn't create any effect, what's called the coma effect. I will explain that later. So if you do that alignment and do it well, then you can get to 0.1. Most people can get it to 0.2 without too much trouble if you understand what you're doing or just being told what you need to look for. The third type for the divergence and convergence, that comes from the fact that the distance is not ideal. We have a sample sitting in certain places, so your beam would go diverge and converge. Depends on where the condenser aperture is relative to the length and imperfection of the lens and that sort of things. All comes together, give you this type of beam field. So we have measurements of this on our microscope, which is F20, 200 kV. You can also do calculations. This paper has a formula that shows you how to do this calculation. You can also do the measurement yourself. But you need to know your microscope parameters. So we know that if I have a 1 micron beam, at the edge of that 1 micron beam, I will have 1.3 milliradians of beam fields coming from the divergence, the convergence of the beam. If I'm using a 50 micron C2 aperture, so you use larger C2 aperture, then this will be bigger for the same size of a beam. For the spiral one, there was a paper that gave a number of being 0.03 milliradian at the 1 micron beam. So that's relatively a small effect. In what I'm going to talk about, I'm not going to consider the source size, and we are going to combine those two as one effect when we are describing it, because both of those are sort of depends on the radius of it. So the radius, let's say you have a beam this big at the middle, and at the middle, let's say your actual beam field, that's this turn over here. If this is perfect, then the middle of it is it doesn't have a tail. As it go out in radius, then that number will increase. So that's true for both this one and this one. So we will make it together when we are looking at it. Okay. This probably is the talk with most equations. Okay, and you go back to the first day when Henning talked about the Fourier transform. So this is a lot of things that are coming out from there. But in a little different form, just so that I can give you an example. Now, if you are doing X-ray crystallography, in which you are not forming image, in the Fourier space, you will talk about having a structure factor that got an amplitude and also have a phase that coming from your structure. So that's what this part is. So this is actually looking at I think it's the wave functions of a pair of diffraction pattern. Let's say you have a diffraction spot at 1, 0 and the minus 1, 0. Then to combine the contribution from those two, you get something like this. We want to write it in this form for convenience later. So it has a structure part, which is this whole thing. Okay? And it has in that there is an amplitude, and there is a phase value that depends on this. This is coming from Fourier transform, so it's at the dependence of two things together. Like what Henning was talking about. If you look at it exponentially, it's what he has. I'm only looking at look at it in a little differently. So here, then the second part is the phase of that structure. Okay, so sometimes this is referred as a crystallographic phase for the reason I just said. In X-ray crystallography, you only have turns up to this point. They don't have what is going to become the contrast transfer function part. So they will only be looking at this part. So we are doing imaging. So at this point, when you are in that Fourier space, you apply your CTF to it, and that looks like this. It's a sign of a wave aberration. Okay, so there are two terms in that. One is, so usually we only have to worry about this. We correct for transfer, contrast transfer function, then we will get the same as what the crystallographers, X-ray crystallographers will get. So that's what happens when you have bin tilt of 0. When your bin tilt is not 0, so no matter what source that's coming from, the Friedel-Mays no longer are equal. Okay, they are not the same as the other. So when you are making this turn, there are certain turns doesn't get canceled out. So if you are looking at, there's one turn for the positive number and the positive part of one of the Friedel-May, and then that minus as the other one, contribution from the other one. Then you actually have to write it in this form. So this gamma, instead of one value, you also have to know what's the positive, what's coming from positive, what's coming from negative. Take the average of that looks like your CTF. Same with this phase turn for the structure. There's an additional turn. You see, it up to here looks like the crystallographic numbers. And then you have to add another phase to it. And this phase, because they are not equal, it doesn't cancel out. So when you have bin tilt, you have an additional phase shift, and then you have a different numbers that you have to put in your CTF. Okay. So as I said, because of that two turns, so you have two effects. Sometimes people say 3. You have a defocus change from that, because those two add together divided by 2 don't actually be in the same as when you don't have it. So, and the other thing is that bin tilt is directional. Let's say if I have bin tilt turning over this direction, then the defocus or CTF doesn't actually change in the direction I'm perpendicular to that bin tilt. Okay, so as a result, the effect is not isotropic. So you will create estigmation when this effect is taken into place. So I'm showing what it looks like. So if you have 0 tilt here, and the other things that it will create an image shift in there, which I didn't put in the formula there, but it's part of that. So 0 tilt, if I look at 5 milliradian tilt, it moved a little bit. I hope you can see that. It moved a little bit, and the bin tilt is obviously in this direction because that defocus changed a lot. Okay, the direction that's perpendicular to the bin tilt direction didn't actually have much change to it. Okay, whatever we are seeing there is some side effect from other things. So that's what you expect. When you have a bin tilt, you're going to have a different defocus and estigmation as what you would have gotten without that bin tilt. Okay, so that's what you will get. This is actually is not a big problem because number one, the changes is relatively small for the amount that we were looking at. So this 5 milliradian, as I was saying, that we can easily do 2 milliradians even with just rotation center alignment. So this 5 milliradian, this is really extreme cases, and I'm using really low defocus. That's why I can show you with such a dramatic effect. Now, the normal range that we are doing things, the amount of estimation defocus changes is small. And also that it's just a CTF value. You can just estimate estimation instead of without it. So internal processing, it doesn't make any differences whether it comes from bean tilt or it comes from a genuine estimation, okay, and defocus change. However, that effect is being used to our advantage in a way that we can use that to align the bean tilt. Because as you can see before and after of bean tilt, I look at the image itself. It's not very obvious what I have changed. But if I look at the Fourier space, the tone ring, and all those things, it becomes more obvious. Plus, the way it changes, let's say the defocus changes with and without the bean tilt, is proportional to the square of the amount of tilt. That means that it moves really fast as if you give it more tilt, the effect will become more prominent very quick. Okay, so that's good. That's really good, because what we can do is that in order to determine the bean tilt of certain value, say for example here, I have a case where I don't know what my bean tilt is. Even I determine this afterwards. Okay, and I try to adjust my objective estimator so that they look round in both cases. So they look all perfect. So I cannot tell what's going on if I don't do anything about it. Now, if I start tilting, then I will be able to tell whether I have tilt or not. Because if I apply a 5 milliradian bean tilt in one direction and the opposite direction, I start off with 0 tilt. This turn is symmetrical to 0. So these two effect in the defocus and estimation will be the same because they are centered around 0. This one, which I start off with some tilts, I'm going to end up seeing that a big differences between this plus 5 milliradians and the minus 5 milliradians tone range. Okay, so I can look at these two differences and be able to say, if they are different, then I have some bean tilt that's in the original one that I need to make adjustment of. Then you would do that until you get to this point. Then you keep on comparing what it gives you when you induce extra bean tilt to it. Then you'll be able to align it to 0. The comma-free alignment procedure you've seen in FEI software, Gatan software, and all of their softwares are something like this. It all depends on how they present it. I remember trying to do the FEI one. It says, it start wobbling between the bean tilt and said, try to make them similar. And that is what this means exactly. That when you really have no bean tilts, this two will look similar. It looks similarly bad, unfortunately. So if you just look at the image, it's difficult to tell. Better softwares like what's in Gatan, they would do a Fourier transform, give you a power spectrums. Then you look at it in this form, then it's easier to tell where you are. Okay? So that's the defocus effect and estimation effect. The second one that is a little more problematic to us. In this case, let's say I didn't know I have bean tilt. Then I do my processing. Maybe I see some estimation. I do our normal CTF correction to it. That's fine. Now, even though we cannot tell where the source is, the effect is the same in terms of where I'm going to have phase shift. When I'm the 100-degree phase shift or phase flip. So that's going to be the same whether it's comes from objective estimator or it comes from bean tilt. So as far as that, that's the same because they all go into the same turn in the CTF. The crystallographic one, which This is the same equation I showed before. This is the CDF part. This is the part I just talked about. This is the crystallographic part. The additional phase shift in the crystallographic phase in here is a harder thing to correct. You don't, that basically changes the structure you are looking at. Let's say you don't consider that part, then you have certain beam tilt, then your reconstruction will look distorted. Okay? So it's going to be a problem. And not to mention that in many cases, if you have certain kind of your structure in one experiment, let's say we took one image today that has one beam tilt, I get a reconstruction out of my image that's been distorted. Next day I take another image which has a different beam tilt. These two structures are not going to look identical because it has the effect of the beam tilt in its phase shift in there. Okay, so that creates a problem when you try to merge this and you try to get the right answer. This term, the phase shift, you can write it out in a formula like this. The way you look at this as so there's a spatial frequency term in here that says that this is proportional to cube of spatial frequency. In other words, the higher the resolution is, then the larger the phase shift is. And it's not just linear, it's to the cube. So it goes up really fast when you go to high resolution. When you're at the lower resolution, it's almost have no effect. Okay? So most of the time, you start to worry about this when you get to about 5 angstrom resolution. Beyond that, you start to get serious problems with it. The second one is that it's proportional to the displacement of the diffraction spot from the center of the operation. In other words, that's a way of expressing the tilt angle. That's divided by the wavelengths of the beam. There's also a term of spherical aberration constant that we talk about. So if this is 0, then it's not going to cause any effect in your image. Now we want to look at what this is doing. And this term here basically just says that this is direction dependent. So if you are determining this in certain direction, you want to see whether it's parallel to your beam tilt direction, or I shouldn't say parallel, but sort of in the same direction as it goes to. Or if you are perpendicular to its projection, then it really doesn't do anything. Okay. So to sort of give you a feel of what this looks like, I made this. It's a bit exaggerated because all the edges here are just straight lines. Have then separated in different distance. I'm simulating that as if this is separated by 2 angstrom, that's 4 angstrom, that's 8 angstrom, and the cube size is also that same number. Now, if I apply a 0.2 degree milliradian, 0.2 milliradian of beam tilt, then you start seeing that it's as if the center shifted a little bit. Okay? See? And also, there's a tail coming out of it. Okay? That is what they refer as coma effect. It looks like a comet. Okay, it got a tail to it. Okay? So, that comes from the part of that comes from the phase shift. Now, if I increase that even further, the effect is even stronger. And you see that now if I have something like this and I try to determine the position of all this cube thing, I'm going to be off on all of them. And I won't be able to tell the I have a bigger trouble with the one at higher, trying to figure out what's that separation. The part over here is become less and less obvious, the gap in between those. So that's what happens. You go to higher resolution, it becomes a bigger problem. Okay. So far what I'm talking about are apply to any kind of beam tilt. You have a certain value, it's in certain directions, and it does the same thing. Now I'm going to come back to this different type of beam tilt. And as I said, I'm only going to discuss two of them. So the first one is the axial beam tilt. So this is basically assuming all your beams parallel, or should I say that it's the average value of whatever your beam tilt is of your whole beam. So auric tilt that Richard Henderson wrote has the ability of determining this value and make correction of it. Okay, so what do they do is that the first idea, without knowing what it should be, now you have to figure out how to start off. So they, of course, at the time they worked on bacterial reduction that got symmetry to it. Okay, so this has P3 symmetry. In other words, let's say I have a tilted image. I'll have a spot here, 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 and it's predominant over there. These three are related by their symmetry. Okay, all three, and they are related with symmetry. So crystallographically, they will have phases that has exact mathematical relationship. Like when you merge, you can convert that into the same value. Okay. If you have beam tilt, then if you don't have beam tilt, then you have exactly this situation. If you have beam tilt, then that's not true. What I'm plotting here is a way that I'm trying to express the beam tilt value as a cosine. I express it as a cosine so that I don't have to worry about 180 and the minus 100 being the same. And so as a cosine, as zero beam tilt, or zero beam tilt and this zero spatial frequency. So at the center of my power spectrum, that would be a value that would be 1. Let's say that would be 1 because I'm plotting cosine. As I go out in spatial frequency, that will decrease. At some point, it's going to reach 90 degree. Then it becomes dark. Or actually, becomes dark and gray, I guess. Gray, and then becomes dark. Because it can go to -2. So by this time, it becomes a minus. And then it becomes positive again, and it will get to 1 again, and go down. Let's say we have this pattern in there. As I said, it has a directionality to it. This is the direction of the tilt, so I have this effect. If I look at the direction that's perpendicular to it, then it's always 1. So there is nothing that's in the correction. So I have a pattern, diffraction pattern sitting on here with that effect there. Then this 3 point that used to relate to the purely by symmetry relationship are no longer going to have the same value. You will have a bigger value. You will have a bigger shift here. You have less shift there. So as a result, those symmetry-related refractions no longer have the same value. So we can use that to determine the beam tilt. You have well-determined phase value for these 3, and then you can say how are they different by what amount, and if you have a bunch of them, you can average the effect, then you can come up with an overall beam tilt, an average beam tilt that's determined by this method. Then what they would do is apply exactly this formula to shift it back for a given frequency. So that's what they could do once they determine that they can do that. Now that's the best situation. You have symmetry-related ones. Now, if you don't have a symmetry-related one, it becomes a lot harder. If you have a K1 symmetry, that's going to be harder to do. I don't think they have done this on ones without any symmetry. They've done this on ones that has some symmetry to start off. So you can take your untilted data, determine this first. And once you have those, then you can start use references from the ones that you know what the phase value should be, and what you know what the bin tails are. So once you have that, then you'll be able to start. When you have some information, then you'll be able to do something like this. So that's the second thing that they do. Then the third one, just like any of the auric-tailed refinement, at a certain point you accumulate enough information, then you can take something that's not at the same, you don't even know the phases, but there are some common points that you can relate it to. So the same as the way we are doing origin refinement. Then you can use those references, your references from your accumulated informations to determine that the same bin tail value. Okay, so this is what the way that it's used in auric-tailed. Because of the way it's using it, and it's being applied to our data in our phase and the amplitudes in the Fourier space, which is a collection of average of everything in your image. So it only has the ability of correcting the axial bin tail. It's not being able to, it won't be able to do anything about the bin tail caused by divergence or convergence, the ones that's actually has effect from the rate, which will be different, depends on the radius of your location on the image. So that's an important point. It only does the actual bin tail. It doesn't actually do anything about the divergence. Now, we're going to think about what will happen with divergence case. When you look at the divergence, you can think about that, let's say our overall bin tail to the actual one is 0. Then on certain part of my bin, I got a positive value. Here again, I put it to 1 milliradians going this way. And it's the same equation as we were looking at before. It was determined by the magnitude and the frequency. Now, your bin have, there's a bin going this direction, there's a bin going that direction. You always have a mate. So there's another one that's going -1, okay, when you have a divergence case. So if you add the effect of those two together, you end up kind of a cancellation in terms of its deviation from the original phase value. So what is going to happen then is that the combination of the two will damp your original structure factor. Let's say this is the structure factor of some refraction that you have there. You got the direction of this, and it have a magnitude of that length in white. Then by applying that bin tail, which only changes the phase in both positive and the negative direction, it's going to end up giving you an effect that basically make it shorter. Okay, but the direction doesn't change. In other words, instead of getting a phase shift, we are getting an amplitude change. So as you tilt it more, then it becomes smaller and smaller and smaller. It went too far. So at some point, it's basically going to disappear, right? It gets to 90 degrees. Individually, it becomes 90 degrees. Then that's phase, the structure phase is no longer there. The structure factor is no longer there. So in a way, when you think about the convergence and divergence, it's actually, when you look at this effect on our average structure, it's actually like a B factor type of thing. It's damping down the contribution at that frequency. So if you look at the images that I created here, so I'm trying to show you that effect. With plus direction, we see the common effect that we talked about before. You go to minus, it's going in the other way. You add the two together, the center of your peak becomes the same as the original. You get some effect, some kind of an effect on both sides, but the position doesn't change. And to the definition where it went dark is still dark in almost about the same way. So, because this is more like a B factor effect, it no longer affects the phase, in a way that its problem, you may say, to our structure determination is less, because our structure is more sensitive to a phase change than an amplitude change. Okay. Now the last, Henny asked me to think about to talk about the spot scanning and how does that affect the beam, how does the beam tail affect that? So from my reading, of course, we know that spot scanning has this advantage of it gives you less of the beam-induced movement, and then you can use dynamic focusing when it's tilted, so that it makes it easier to look at the tilted images. You don't have to correct for the defocus gradient. So the problems that can come with it is that the first is that you need to figure out the right intensity per exposure, in the exposure time per spot, because then you have to condense your beam to pretty small, so you need to make sure you're not making it so bright that it saturates your film or your detector, that sort of thing. So that you just have to take care of it. And the second problem, possible problem, is that because you are condensing the beam more, the more you condense the beam, as this is the way we normally use it, it will make the beam divergence or convergence bigger. So the wider your beam is, the more it is look like a parallel beam. So since you have to make it smaller to do spot scanning, so you will get more of that divergence. And this value is high tension dependent. This book, the greatest book, has a very good section on it. So I'm not going to repeat what's in there. They got numbers for all the for several conditions for what you shouldn't be using. You don't want to reduce your beam to certain size if you're at this high tension and at that high tension. All sort of information like that. So you should look it up if you are you want to do this. Now the second part is that if you are using film, you basically only shift the beam. You don't actually do an imaging shift, which brings the information you are looking at back to the center. So that's a little better because you don't produce a beam tilt just when you are doing image shift. When you have to do image shift, like in the case that the spot scanning has to work for digital camera because the area is smaller. So they will use a beam tilt in combination, a beam shift in combination with the image shift to bring the beam back to the center. So when you do that, then you do have a beam tilt being induced in there. This is axial beam tilt, not just divergence. So you're going to have an axial beam tilt in those. So you need to check the amount that is done to make sure it's not creating more problem than it's giving you the benefit for. If you ever want to figure out what it is, you just have to induce some beam tilt. As I said early on, we use the effect of a defocus change and astigmation change to our advantage to decide if something is tilted. So if you induce an extra beam tilt and a minus direction, the same kind of beam tilt, same magnitude, then you will be able to see if they produce the same kind of astigmation and defocus effect. Then you know how much of the value that you have changed. You can calibrate that to find out the whole thing. So that's that about the spot scanning. So for summary, we have two types of beam tilts that I discussed. The first is axial beam tilt. This will create an isotropic defocus change that will look like astigmation, and this induce astigmation. And it will also create a directional crystallographic crystallographic phase shift for the structure. And you can determine that from symmetry related to diffraction spot phase of high resolution diffractions. You don't want to do this for low resolution. So one thing that's in Richard's paper, he mentioned that they would do the tilt geometry refinement and all the outer origin shift refinements to certain resolution, say 6 or 5 angstrom, and then use only the high resolution part to do the beam tilt refinement. This way, then it's not going to try to change everything. And the second part, for the beam divergence, the effect of that is going to be an isotropic effect, because we will be taking molecules in all over our micrograph to create our average structure. So each of them is receiving different divergent beam tilt. So it will create an isotropic tone ring drawing. So you get to certain resolution, and then it pretty much all disappeared beyond that. So it looks like you have a B factor not in the same, not the exact same. It's not exponential, square, that sort of thing, but basically a damping of all of the amplitude. So that's it. Questions?
Yeah. I was just wondering if Richard's original sort is also able to, is it able to correct for every symmetry?
It should be able to.
Because if I just consider the example that you showed, I mean, you had this hexagonal thing, then it's clear that the three symmetry related spots that they would have, because they have a different effect. If I now imagine a square one,
it will be able to do that as well. Well, if you are perfectly aligned to that axis, then you have problem, because it will always be the same. Yeah, but most of the case it's not. It will orient it in one way or the other. No, there's still differences to it. Okay? So in most cases it will be okay, but I don't know how it's going to do P1 if you don't know anything about it to start off. Yeah, but one way you can do is that now, when they started doing that, they didn't know that it's causing this kind of a problem. Okay, so they probably didn't do coma-free alignment at the beginning. But now you know there's such an effect. When you really get to that resolution and then you have a P1 symmetry, unfortunately, then what you can do is do a really, really good beam-tailed alignment first, and then you'll be able to use that as your reference to start off.
So if you use a CS-corrected microscope that doesn't have a CS value,
Right.
this should not be a problem. Right?
Exactly.
But there was this thing, if I'm not mistaken, that the CS correction works out to a certain radius in the objective lens diameter only, and from then on it's much worse than if you wouldn't touch that or grab it. I'm sure.
Yeah, that I wouldn't know.
No, so the CS correction completely fails if you go out of the center of the objective lens.
Mm.
So you talked about the divergence, right?
Mm-hmm.
And the effect that it dampens the amplitude.
Right.
But you haven't said that there's any connection. So could you just determine the dampening?
You probably can, but then after a while, so when it reaches, let's say I have 1 milliradians of this. When the beam that has 1 milliradians of beam tail, the structure there, it will reach where it goes to 0 because it starts phase 15. Earlier than the beam that's inside. So it's a bit harder to do that correction now that we already do the average. So theoretically, it should be possible to do that on your original image before you even do any averaging. I don't know in reality if it works or not. Now we tried some of this on single particle, and it didn't work out very well. The peak that we got at the end wasn't better. The resolution we got wasn't better, or it's just insignificant differences. So maybe the correction wasn't done right, or there's some as you transform, forward and back with all these formulas, maybe somewhere that something is not quite exact. So it actually lost some resolution. Anything else? Okay.